Hello, Dr. Lee. So this is Ethan Fromer and Ben Terry with our progress on the OTA. So looking at starting with our noise budget and capacitance values. So from the project definition, the SNR is 7060 dB and beta has to be 1 over 16. The things we chose are the dynamic error and static error to be 0.1% and 0.2%. I think now we're kind of realizing we need to relax a little bit on that spec in order to decrease the GM required of our OTA, but we'll get more on that later. And then we chose a clock frequency of 60 megahertz just because it was greater than 50 megahertz, so we're not really sure if that's feasible or not. And then as far as our settling goes, we went with 80% of 1/2 of our clock period. And then by running through the calculations, we got our capacitor values here. So CS is 409 femto, and then CL and CF are 51 and 25, about 25 femto. And then there's our CL total. And from that, we kind of get the values of our OTA. So we get our GM to be 1 millisiemens and our AV to be 8,000 and our loop gain bandwidth product to be 1.04 gigahertz and transient frequency to be 40 gigahertz.
And to calculate those values you just saw on the previous slide, we first solved an equation by hand and plugged that into MATLAB so you can see the code here. So basically what we're starting with is our signal noise specification that we're trying to meet, 76 dB, and assuming a temperature of 290 Kelvin. And then from that we solve for the output referred noise of the capacitors, and that's the factor that you see. Then we input refer that by dividing by our gain of 16 squared. Um, and then from that we have our CS, and from CS capacitance we can derive CF, CL, and then CL total. And then we move on to calculating what gain, AV, and transconductance GM that we need to achieve the figures of our static and dynamic error that we set. And those are pretty simple calculations. And yeah, that about wraps up how we calculated.
So then we set up the ideal test bench with the ideal OTA, and we plugged in our capacitor values that we just calculated, as well as our GM into the OTA, and then we just picked a GM over ID to be 15, and then we ran a transient simulation just to see what the output would be. So this is with an input of differential sine wave and centered around 600 millivolts, and then the output gave us the quantization error shown here at the bottom. So we think that because of that, this setup is working correctly. But then when we try to run the DFT, the FS over 128, this is what we get, and we know this isn't exactly right, but we think that it's something to do with the DFT alignment. So we're still working on trying to get this to be, I think it was 85 dB for the SNR. Right now this is giving us I think it was like a 47 dB for SNR. And a similar thing for when we change the input frequency to FS times 63 over 128. I think we're still working on getting the DFT alignment right for this part, so we're not 100% sure on that. And then as far as our OTA topology that we went with, right now we kind of just started with a diff pair with an active load, and part of that is because of kind of the simplicity of the design. We wanted to just see if we could get some gain out of it, and when we run a transient simulation on ROTA with a differential input still centered around 600 millivolts, we get this weird negative 1.75 volt DC offset, and we think it is because we need to add common mode feedback in order to stabilize this. So we're still working on trying to stabilize this, but we think this will provide enough gain if we relax on our settling time our dynamic error and our static error specs a little bit. So that's our plan for the next week, is to relax on our spec for dynamic error and static error, and then recalculate some of our values so that we can see if we can get enough gain out of the diff pair plus the active load. And that's all we have right now. But we'll definitely be coming into office hours and talking with the TA to try and get this resolved. So that's it for now. Thank you.